Welcome to the Deep Dive. We're here to break down the big, complex systems that make the modern web work, getting right to the core ideas. Today, we're tackling something vital but often overlooked: API rate limiting and traffic management.
Yeah, it's like the hidden traffic control for the internet. Every time you use an app, make a payment, refresh a feed, there are just tons of requests hitting servers. Rate limiting is what keeps everything running smoothly, prevents collisions, basically.
That's a great way to put it. And the scale is just immense, right? So our mission today is to really pull out the essential insights on how these distributed systems handle all that traffic, how they stop abuse, keep things fair. We want to go beyond just, okay, set a limit and look at the clever algorithms and architectures places like Amazon and Stripe are actually using.
Exactly, because how you design your rate limits fundamentally shapes your platform's capacity, its reliability, even its security posture. It's foundational for scaling digital services today.
Okay, let's start right there. The basic definition: what is API rate limiting?
At its core, API rate limiting is essentially a control policy. It dictates how many requests a specific client, we identify that client by, say, an API key, maybe a user ID, or just their IP address, how many requests they can send to an API endpoint within a specific time frame.
Right. And you mentioned it's not just one thing. There are like three main reasons why this is so critical. It goes beyond just security. Yeah.
Oh, absolutely. Security is just the start.
Yeah.
First, yeah, it's abuse prevention. It's your first line of defense against things like DDoS attacks, web scraping bots, brute force login attempts, that kind of stuff. Second, and this is huge for stability, is infrastructure protection. It stops your backend systems, which can be expensive and sensitive, from getting totally swamped by sudden traffic surges, whether they're accidental or malicious.
Keeps the lights on, essentially. And the third point, that sounds like it's about playing nice.
That's fair usage enforcement.
Yep.
Crucial, especially if you have many different users or tenants sharing the same system. It makes sure that one noisy neighbor, one client sending tons of requests, doesn't just consume all the available capacity and degrade the service for everyone else. It keeps things equitable, often tied to different service levels or tiers. And if someone does go over their limit, the standard way to signal that is with the HTTP 4219 too many requests error code.
Okay, 429. Got it. But let's unpack some terms here, because I definitely see these getting jumbled. Rate limiting, throttling, and quotas. They all seem to limit things. But how are they actually different in practice?
Good question. They mainly differ in how they control things and over what kind of timescale. So rate limiting, as we've been saying, is generally the strict, often security-focused one.
Yeah.
Think short-term frequency control, like you get 50 requests per second max. Its job is that hard enforcement. It leads to that immediate, nope, too fast, rejection, the 429. It's about failing fast.
Okay, rate limiting is the bouncer at the door. Strict limit, immediate rejection. What about throttling then?
Throttling is more like the traffic manager inside the club, maybe smoothing out the flow to the bar. It's more flexible, often dynamic. It kicks in during surges, maybe deeper within your system, like in a microservice setup. Instead of outright rejecting requests, it might slow them down or queue them up temporarily. Think message queues. The goal is more about maintaining steady performance and user experience by managing latency, rather than just blocking requests cold.
Okay, so throttling tries to manage the flow, maybe make things wait a bit, while rate limiting is a hard stop. And quotas, that sounds longer term.
Exactly. Quota management is about the total volume over much longer periods, like a whole day or more commonly a month. This is where it ties directly into the business side. Your basic plan might get, say, 100,000 API calls per month, while your fancy enterprise plan gets 10 million. It's about total usage allowance.
Makes sense. Now, about that 429 response. If my request gets rejected, it seems intuitive to just try again right away. But you're saying that's a bad idea. What does the server need to tell the client?
Yes, retrying immediately is often the worst thing you can do. It just hammers the already struggling server. The absolute critical piece of information the server must include in that 429 response is the retry after header. This header tells the client exactly how long, minimum, they need to wait before trying again. It's vital for building resilient clients that don't contribute to the overload. Ignoring it is just asking for trouble.
Okay, retry after. Essential. Let's switch gears now to the engines behind this, the algorithms. How do you actually count and enforce these limits? Because I imagine the choice here impacts performance, memory use, fairness, too.
Absolutely. The algorithm choice is crucial and involves trade-offs. There are, let's say, three main approaches people typically consider, each with pros and cons regarding efficiency versus accuracy.
Let's start with what sounds like the simplest: the fixed window counter.
Right, the fixed window counter. It's very straightforward. You just divide time into fixed blocks, say exactly 1 minute long. At the start of each minute, the counter for every client resets to 0. Super easy to implement, very low memory cost. But it has this one significant flaw, often called the boundary condition problem.
A boundary problem. How does that work? If my limit is, say, 100 per minute, how does the edge of the minute cause an issue?
Okay, imagine the window resets right on the minute mark, like at 1.0000000 p.m. sharp. A smart or maybe malicious client could send all 100 allowed requests right at the very end of the previous minute, say at 12.59.59 p.m. Then, immediately after the clock ticks to 1.0000000 p.m. and the counter resets, they send another 100 requests at 1.000.01 p.m. So within just a 2-second actual span, they've effectively blasted your service with 200 requests, double the intended rate. That can easily overwhelm things.
I see. That edge case could be really dangerous for busy systems. Okay, so if the fixed window is vulnerable to that kind of burst at the boundary, what's a more robust approach used in production?
Well, this is where the token bucket algorithm comes in. It's really popular, used by giants like Amazon and Stripe. Imagine each client has a bucket. Tokens, representing permission to make a request, are added to this bucket at a steady fixed rate, say 10 tokens per second. When a request comes in, it needs to take 1 token from the bucket. If the bucket's empty, the request has to wait or gets rejected.
Okay, so tokens refills steadily. What's the big advantage there? It seems like it still limits the average rate.
The key advantage is how it handles bursts gracefully. If a client hasn't made requests for a while, their bucket fills up with tokens, maybe up to a certain maximum capacity. Then, if they suddenly need to make, say, 50 requests really quickly, they can. They just use up those saved tokens in a burst. After the burst, their rate goes back down to the steady refill rate. It allows flexibility without the boundary problem.
Got it. So Token Bucket handles bursts well. But what if you need something that's really fair, like avoiding that fixed window issue, but maybe you can't afford the potential memory cost of tracking every single request timestamp, which I gather is another way?
Right, you touched on the ideal versus the practical. The absolute most accurate method is the sliding window log. It literally keeps a timestamp for every single request within the window. Perfect accuracy, but yeah, potentially huge memory and computation costs, especially at scale. So the clever compromise, the sort of hybrid solution, is the sliding window counter. It aims to get close to the fairness of the log method without that massive overhead. It typically works by keeping track of counts in the current window and the previous window. Then it uses a weighted calculation, sort of like linear interpolation based on where you are in the current window, to estimate the rate across the sliding time frame. It smooths things out and avoids that sharp boundary issue of the simple fixed window. Much more scalable than the full log.
Okay, that sliding window counter sounds like a pretty sophisticated solution for high-volume systems. So we have good algorithms now. But here's the next big challenge. Most real systems aren't just one server. You might have 5, 10, hundreds of API gateway instances. How do you stop a client from hitting the limit on each instance, effectively multiplying their real limit by the number of instances? That consistency problem seems really tough in distributed systems.
You've nailed it. That's the classic distributed systems headache. You have to distinguish between local versus global rate limiting. Local means each gateway instance keeps its own counts. It's super fast, low latency, because there's no network call needed. But like you said, consistency is terrible. If the global limit is 100 requests a minute and you have 5 nodes, the client could potentially sneak in 500 requests. Not good.
So for real enforcement, you basically have to go global, even if it means taking a performance hit.
Pretty much, yes. Global rate limiting requires some kind of centralized service. Let's call it a rate limit service, or RLS. Every single gateway instance before processing a request must check with this central RLS to see if the client is still under their limit. This ensures consistency across the whole cluster. Of course, this adds latency because it's a network call. That's why something really fast like Redis is the go-to choice for the central RLS store. Its speed helps minimize that latency penalty.
Okay, Redis is the central source of truth, but hang on. There's still a race condition possible, right? What if 2 different gateway instances both check Redis at almost the exact same microsecond? They both see the client has 1 request left, they both let the request through, then they both tell Redis to decrement the counter. Boom, you're over the limit again. How do you solve that?
Ah, yes, the concurrency problem. This is where atomic execution is absolutely crucial. And the standard way to achieve this, especially with Redis, is using Lua scripting. Atomicity means the entire sequence, read the current count, check if it's above 0, decrement it if it is, and write the new count back all happens as a single, uninterruptible operation within Redis. Lua scripts allow you to package that logic and tell Redis, execute this whole block without letting anything else interfere. That guarantees no two instances can mistakenly approve the same last request. It ensures perfect consistency at that critical moment.
Wow. Okay, so that atomic Lua script execution in Redis is really the linchpin for making global rate limiting actually work reliably at scale.
It really is. And just to add one more piece for scaling that central RLS itself, especially if you have millions of clients, architects often use consistent hashing. This is a technique to distribute the client keys, like API keys, across multiple Redis nodes or shards in a predictable way. It ensures that, most of the time, a specific client's data lives on the same shard. This minimizes disruption and data shuffling when you need to add or remove Redis nodes to scale the RLS out. Makes the whole thing more manageable and resilient.
Okay, that makes sense. Let's bring this down to earth a bit. Where do you actually implement this in a typical setup? Putting this logic inside every single application service feels inefficient.
You're absolutely right. You typically want to handle this at the edge, at the infrastructure level, to protect your application servers. A common place is in your reverse proxy or load balancer, like NGINX. NGINX has built-in directives like limit tray zone that let you configure rate limits. It often uses something conceptually similar to a leaky bucket. And crucially, it often has a burst parameter. This allows NGINX itself to queue up a certain number of requests that exceed the steady rate, acting as a buffer before rejecting or overwhelming the upstream application.
Right. Shield the application. What about the big cloud providers? Like if I'm using AWS API Gateway.
Yeah, cloud gateways are designed for this. AWS API Gateway, for instance, uses the token bucket algorithm internally. You configure limits through something called usage plans. These plans let you define specific throttling rates and also quotas. Remember those longer-term limits. And you can tie these usage plans directly to different API keys or customer tiers. So you can easily give your enterprise customers a higher burst capacity and overall quota compared to free tier users, directly mapping the limits to your business SLAs.
That integration with business peers is key. Now, another point of potential confusion people run into, rate limiters versus circuit breakers. They both sound like safety mechanisms, but they do very different jobs, don't they?
Completely different, though, complementary. They protect different ends of the conversation. The rate limiter, as we've discussed, primarily protects the callees, the service receiving the requests. It stops the service from getting overloaded by too much incoming traffic. It's an inbound control. The circuit breaker, on the other hand, protects the caller, the service making requests to another service, a dependency. If that downstream dependency starts failing repeatedly, the circuit breaker opens or trips. It stops the caller from pointlessly hammering the failing service, preventing cascading failures, and giving the dependency a chance to recover. It's an outbound control focused on failure.
Got it. Limiter protects the service being called. Breaker protects the service making the call from a failing dependency. Okay, back to the client side for a moment. You emphasize the retry after header. But what if, for some reason, the server sends a 429 but doesn't include that header? What should a well-behaved client do then? Just give up?
No, not give up, but definitely don't just retry immediately or repeatedly. This is where the client needs its own resilience strategy, exponential backoff. If retry after isn't provided, the client should wait a small initial amount of time, then retry. If that fails again, it should wait longer, maybe double the previous wait time, then double it again if it still fails. So wait 1 second, then 2, then 4, then 8, and so on, usually up to some maximum wait time.
Exponentially increasing the wait time. That makes sense to reduce pressure. But what if thousands of clients all hit the limit at the same time, and they all start their backoff calculation at the same instant? Will they all retry simultaneously after 1 second, then 2, then 4?
Excellent point. That could create synchronized waves of retries, basically recreating the overload problem. That's why the other crucial part of exponential backoff is adding jitter. Jitter means adding a small, random amount of time to each calculated backoff delay. Instead of everyone waiting exactly 4 seconds, they wait maybe 4 seconds plus or minus a few hundred milliseconds, randomly. This randomness spreads out the retry attempts, smoothing the load and preventing those synchronized retry storms. Exponential backoff with jitter is the gold standard for client-side retry logic.
Exponential backoff with jitter. Okay, good practice noted. Let's tie this all back to the business level, especially in multi-tenant systems where different customers pay for different levels of service. How do rate limits play into that?
They are absolutely fundamental to it. It's not just about technical stability, it's about delivering on business promises and managing costs. You need strict tenant isolation in your rate limiting. This means the limits applied to one tenant customer A, shouldn't be affected by the usage of another tenant, customer B. The limits need to be tiered based on the service level agreements, SLAs, you have with each tenant. This prevents the noisy neighbor scenario we talked about earlier from degrading the quality of service, QoS, for your premium customers. So rate limiting becomes a tool for enforcing QoS, aligning technical capacity with contractual obligations, and also managing your own costs, especially if you're paying for underlying resources based on usage. It caps the load in a predictable way.
It really is a mechanism that touches everything from deep infrastructure up to the business contract. Okay, this has been incredibly clarifying. So for everyone listening, the big takeaways seem to be, for modern high-scale systems, lean towards algorithms like Token Bucket or the sliding window counter for their better handling of bursts and efficiency. If you need cluster-wide consistency, a centralized Redis RLS using atomic loop scripting is pretty much the standard way to solve the concurrency issues. And critically, ensure clients cooperate by respecting the retry after header or implementing robust exponential backoff with jitter.
Absolutely. And maybe one final thought to leave you with, something to chew on. We established that getting that guaranteed perfect consistency requires every single request to talk to that central rate limit service, that Redis instance. It's a network hop right on the critical path. This makes the RLS itself potentially the single biggest performance bottleneck and arguably the highest single point of failure for the entire system's request flow. So the provocative question is, how do you weigh the architectural trade-off? When might it be strategically acceptable to relax the requirement for absolute 100% perfect consistency, maybe allowing a tiny fraction of requests to exceed the limit under extreme load in exchange for potentially much higher peak performance and removing that critical dependency bottleneck? Where does that balance lie for your system?
That tension, perfect consistency versus raw performance and resilience, is at the heart of so many distributed system designs. A really fascinating challenge indeed. Thank you for guiding us through the intricate world of API rate limiting today, and thank you all for joining us on the Deep Dive. We'll catch you next time.